Alright, so in this video we're going to continue with contour integrals, and now we're going to talk about a more general case in which we have a function defined as a function of x. So we have our xy plane, which we treat as the complex plane. So this is the imaginary axis and this is the real axis. And we're going to have a function defined as follows. So this is 1, this is 4. So this is going to be our curve or our path of integration. So this is going to be point 1 plus 4i. This is the point 0. And essentially our curve C is going to be defined by the path y equals to 2x squared. Now what we can do here is we can define this as a parametric curve, because essentially what we want to do is we want to express the following complex variable z equals to x plus iy in terms of just a single parameter. So let's make x, which is the independent variable, equal to some parameter t, and that means that y is going to be equal to some parameter 2t squared. So now that both of them are expressed in terms of the same parameter, we can substitute back in here. Now remember, the limits of t of a parameter when we're taking a parameterization of a curve are going to be the same limits as the independent variable, and in this case that is 0 and 1. Because the independent variable is x, so the limits of integration are going to be coincide with x in this case. So now we have defined this. Let's define z as t plus 2t squared times I, and then our element of integration dz is equal to the following. So that's going to be 1 plus 4t I times dt. So we can now start performing integration. So remember that this is just a path. The integration depends on the function we select. So in this case, I want to perform the integration along of the following functions. So z squared dz. So all we're going to do is we're going to replace all those values that we just found. So z is defined as t plus 2t squared I. So this is going to be squared times 1 plus 4t I dt. So that's our element dz. And now we can just keep performing some expansions here to hopefully reduce this expression to a polynomial that is very easy to integrate. So this is going to become t squared plus 4t cubed times I minus 4t to the power of 4 times 1 plus 4t I dt. And now if we perform another expansion, this is going to be equal to the following. It's going to give us t squared plus 4t cubed I. So I am basically just multiplying this by each of those two elements, this by those two elements, and so forth. And then we're going to get plus 4t3i minus 16t to the power 4 minus 4t to the power 4 minus 16t to the power 5i, all of that times dt. And we can simplify this expression by grouping terms that can be grouped. So in this case we have plus 8 times t cubed I minus 20t to the power of 4 minus 16t to the power of 5i. And now we have this, we can finally start our integration. So this is going to give us t cubed over 3 plus 2t to the power of 4i minus 4 times t to the power of 5 minus 8 on 3 t to the power of 6i from 0 to 1. And hopefully you can see that this is going to turn out very nicely, because that one is just going to make the expression rather easy to calculate directly. So this is going to be what? This is going to be 1 on 3 plus 2i minus 4 times 1, so that's minus 4, and then minus 8 on 3 minus t1, the value is 0, so that's just going to cancel out. So in the end we're going to have this, and we can simplify this by grouping the real and the imaginary parts together. So in the end we should get minus 11 on 3 minus 2 on 3 I. So this is going to be the value of that integral along that curve, sorry, should have the I here, this is going to be our final result. And this works for any curve that is essentially defined as a function of x. So if we have any curve that is y as a function of x, then we can perform this very simple parameterization. And then in the end, what we're going to get is a really interesting integral. And it's going to simplify, hopefully, depending on whether this expression here or not is rather simple. But hopefully this gives you an idea of how you can perform this type of integration for a function of a complex variable. And of course, there are more parameterizations that we need to look at. So in the next video, we're going to go through another example that is going to take into consideration the polar coordinate parameterization. So if we're integrating with respect to a circle, for example, or a semicircle, it is better to use polar coordinates. So in that case, we're going to use a different parameterization to what we have been doing so far. And that's what we will focus on the next video.